So we are here to talk about matrix factorization. It's more of a tutorial kind of talk because I figured that most of you would be new to this, and it's a fairly recent technique. It's been pioneered by mostly by the Netflix contest since 2005. So it's fairly new on the range of all the machine learning techniques. So there are some aliens and iPods, I promise, like definitely. So what's the point, right? So when we're done with this, I just want you to take something away from this talk, and that basically is that this particular technique is fundamental to in machine learning. It's not just like some fancy, advanced technique that's just applied in some niche areas. But I just want you to get an understanding that it's fundamental. Basically, if you look at a building and you go near, you can see the building blocks. But when you see something like matrix factorization, you don't necessarily understand that how it can be a building block, like how it is a fundamental. So when I first learned about sorting or searching, that's how I felt. Why is this important? Like how can this be? It looks like some random arbitrary thing to learn, but eventually over the years you understand that wow, this is really everything comes down to sorting or searching, or even like matrix multiplication, or why is matrix multiplication defined like the way it is, because eventually you'll understand that that fits perfectly for so many cases. So that's exactly the point of this talk, is to understand that it's not just a fringe technique, but it's a fundamental algorithm that you can apply in many different cases. So just to be clear, okay, the alignment is off a little bit. Awesome. So it's just to be clear that we're not talking about anything fancy. Matrix factorization is just what it means. You have a matrix, suppose say a 4 by 4 matrix here, and you want to factor it into a 4 by 3 and a 3 by 4 matrix. So if you just multiply it, and it just aligned a little bit wrong, but it's just a 4 by 3 matrix. I'll just give you like 2 seconds to make sure it's correct. All right, awesome. So that's what we want. We input a matrix and we want 2 matrices, and this 3 is an arbitrary number that we decide on the fly. So depending on certain considerations, we'll come to that later. And so this is a clip from the Wikipedia page about one particular factorization technique. And as you can see, there's a lot going on. Whenever I'm faced with a lot of equations like this, I just go watch some movies. So so that's what we're going to do. Let's just watch some movies instead. So when you're deciding to watch a movie, how do you decide which movie you want to watch? You can't just say movies are just like an action movie or something like that. It's just like saying that you are a male or you're a female. That's a very one-dimensional description. So movies are a mix of many different characteristics, and we just want these are not particularly well defined themselves. Action is very large, blunt description, and action and adventure, they overlap. It's not like action and adventure. You can't have adventure without action. So it's like 2 different genres. So language is a blunt tool, and there are certain classifications which we don't even think about. For example, there are people who wouldn't watch a romantic comedy, but if George Clooney is in it, they'll watch it anyway. So that seems to be a genre which is not captured in any kind of classification or anything. So we'll define something other than just blunt, language-oriented tools. So what we're coming up with is we'll just give it a set of numbers depending on how much of an action movie it is, how much of a horror movie it is, or how much comedy or something like that. So you have something like this, and you can split a person into the same set of factors. How much you like a horror movie or an action movie. So you have this split. So let me see. Okay. So once you have that, different people can have different splits, and once you have that, you can find out how much you like that movie by taking a dot product of those two numbers, right? So that kind of, when you have a horror movie, that's, and just the negative cancels out. So you can see that person one is not going to like this movie very much, but P1 likes it. So this is the basic idea. Instead of using the regular classification of movies, we want to come up with numbers like this. So the next challenge is, how do you figure out what these numbers are, first of all, and then how do you figure out what kind of features? Now, action is still something that needs to be discovered. It's not given to you already. So those are the challenges. And when we go and look into the matrix multiplication again, now how we can look at it is basically, you look at it like this. So on this axis you have all these movies, and this is what, on the top you just imagine some people. So movie 1 and P1 likes it, right, likes it this much. So when you factorize it, what comes out is, these are just, let me back up a little bit. So what this is, it doesn't look like it, but this is just, say on here, this is movie 1, this whole line represents movie 1, and this is movie 2 rating, movie 3 rating, and this is just person 1, person 2, person 3, person 4. So when you have a matrix like this and you split it like this, what you can think of it like, like the following. So movie 1, some unknown feature, this is the preference of this person for that unknown feature. So this is movie 1 feature. So once you have a factorization like this, what it represents is, movie 1 has these factors. Suppose, imagine that this is an action, this is horror, and this is romantic comediness. So when you have a factors like this, you can just think of it as, the movie 1 has been split into these 3 factors, right? And you can do the same thing for people. Like, we have 4 people rating these movies. So this first line is the split of this first person. The second line is the split of the second person. Third is the split of the third person, and so on. So we just started with a rating matrix, and once you factored it into 2 factors, and you can think of it like that. So what makes it okay? You can maybe factorize it in many different ways. So it doesn't mean anything. How can you just come up with a random factorization and just say, think of it like this? So the missing link is basically a theorem that states that this factorization is unique. You can't have many different, once you fix the number 3, you can just have one factorization like that. So that is what makes this particular factoring thing more plausible. So okay, so I'm just going to keep shifting the definition. So basically, you just have a central algorithm, but the more ways you look at it, there are several different ways to look at it, and you'll find people calling matrix factoring like collaborative filtering or SVD. There's so many different things that people call it, but they're just minor variants of a general idea. So I'll just keep, without saying what the name is, this previous thing is collaborative filtering, but we'll just look at the core idea without getting distracted by the names. So the previous thing is, the example is, we had a rating matrix, a bunch of movies and a bunch of ratings, and we discovered the features like action, horror, or any of those things. We discovered them on the fly. So that is just without stating anything about what the features are or anything like that. You can just actually discover those features. Another method is using an internal description. So if you already know something about a certain certain thing that you're trying to figure out about, if you know something, then you can just say that and make features out of that. So this is an opposite. So the advantage is basically you can control it. It's in the previous method, whatever features just pop out of the system. You have to run with it. But in this case, you can actually control what you want to do with it. And if you have a business goal that you want to achieve, then you can probably control the matrix, the features, things like that. And the previous thing is not so possible. You're just flying, and whatever comes your way, you have to accept that. So those are like two different ways of framing a matrix. And we'll just have a demo using the second technique. I'm just looking at the time. All right. So now from movies we are going to transition into documents now. All right. So when you're seeing documents, you can think of the words as the features. So this particular document has these words, and certain words are not that important or things like that. They are not so important. But basically, you build a matrix again, saying in the previous matrix, what we had was movies, and on the top we had users, rating the movies. In here we will have, let's see if we have a slide. Yeah, we'll have a document and the word. And if you have that word, you just count the number of times it occurs in that document, and you put it in there. So this is how you frame a matrix for documents. So I'll just let's try a quick demo. So here are the documents. I hope you can all read. Yeah, it's pretty clear. And as you can see, what I'm doing is I'm asking for the similar documents for the first document, that is human-machine interface for computer applications. So what it returns to me is these four documents seem to be pretty close. The first four, they have a similarity of 0.99, right? And when you read the documents, you can understand that those four documents. Let's say document 1, a survey of user opinion computer. So it kind of very similar to user interface study. So there are two different clusters here. The second one is something to do with graphs, random binary graph, intersection of path trees. So it's able to say that your document is this much similar, and these documents are not very similar. So that's just what it can do. And I'll just have one more demo of so in here what I'm trying to do is I've included a new document, user opinion testing, and I'm just put a new document in there. I'm just going to ask the same thing again. What are the similar documents to the first document? And let's see what happens. And the nice thing here is, so user opinion testing is document number 3, and it says 0.99 similar. So the interesting thing to note here is there is no common words. Human-machine interface, computer applications, and user opinion testing, they don't have any common words in them. But
how do you find out there's a
yeah,
dictionary or?
no. It is able to find out the structure from within, right? So what happens is human machine and say user co-occur in one document, and some other word co-occurred in another document. So it's able to infer from that. And this is just using like 5 or 6 word documents with so little information. It's already able to infer so much. So that's the power of these algorithms. So let's go back to the slides.
So that demo is actually going through full documents and analyzing it, or just the sentences?
No, these are documents. As far as this demo is concerned, this one thing is a document. The sentence is a document.
It's being imported and then analyzed.
Yep. This is all it's taking in. The first is one document, second is the next document. And when it's printing this means that The zero document is, of course, is completely similar, so it gives a score of 1. And the fourth document is 0.9997, similar. So the fourth document is 0, 1, 2, 3, 4, system, human, system engineering testing, EPS. This is just words that I put in there to make a point. But you can see that, it's kind of similar. Actually, this is just, I simplified it by saying that when you have, a matrix, you can factor it into two matrices. Actually, what goes on, in SVD is you have three matrices, and the middle matrix is, it's not that important to understand this particular thing at this point, but this is the full detail. And the middle matrix is something that gives you the strength of each of these features. So you can just ask for the top 5 most strong features, or the top 10 most strong features. So what happens is, basically, when you have, in time domain, it's easier to understand. When you have a time domain signal like this, and you want to make a prediction, you probably will ignore all these local seasonal, randomness, right? So that's the effect of asking for the top 10 strong features. So all the weak features, they kind of get neglected. So that makes the algorithm more accurate. All right, so we come to the aliens part. So this is the complete, third way of viewing. We've already gone through two different kinds of, looking at the algorithm. Basically, one is from external viewpoint. You just submit ratings and it figures things out. Second is you work with the features, and like a document, you just you find out what the words are. So you work from the internal description instead of the external description. And the third is just, one more way to view the the algorithm, which makes it so much more powerful, is that, suppose this is the the example I'd like to give. Suppose an alien comes across an iPod, right? And they want to decipher what this is used for. All they are seeing is just bits and pixels, and suppose they are able to decode the sound that's coming out. And what they are doing is, this much information is coming out, but actual MP3 format is much more smaller, right? So how does MP3 get converted into sound? So when you actually go into that line of investigation, what you can find out is you can learn about human hearing, right? So how does MP3 compress? For example, one thing it does is it keeps dropping everything over 10,000 hertz, because humans don't hear very well over 10,000. So that's right. People. Working back, you can understand the capacity of human hearing. And MP3 also drops, nearby frequencies. If you have like 1,000 hertz and 1,005 hertz, it'll just pick one and drop the others. So that's also depending, because humans can't distinguish less than that particular frequency limit. So when you have compressed data, and you have a reference to how to actually expand it, you can work back and understand a lot about how that, why that compression system came about, right? So let's see how this applies here. So a matrix, suppose the typical matrix sizes that we deal with is about, say, 1 million by 100K. That's 100 billion data points. And say we are asking for 100-point SVD, that yields us approximately 100 million data points. So we are representing the data that was initially contained in 100 billion numbers in just 100 million numbers. Right? That's a compression ratio of 1,000. So using this, you can, this particular compressed data, you can think back and see why are these points clustering together. So you can understand about the domain that originated the data. So that's the data analysis value of this particular algorithm. And there are a bunch of other uses. Suppose you're having a very complex machine learning algorithm, then you can, that is, so to start with, you have like 1,000 variables, but the algorithm is very slow in 1,000 variables. What you can do is just put an SVD in front of it and reduce the number of variables, and you can run the resulting, the algorithm in the resulting set of variables, and it will perform pretty well. It will perform even better sometimes. So another thing is basically is just this can also be used to visualize clusters. So the way to think about it is we are reducing the dimensions. When we are doing compression, you're reducing 100 million dimension to maybe 1,000 dimension space, things like that. What you do is you just reduce it to 2 dimensions, and that will give you something that you can plot on a graph. So these are all just from some use cases. A tag, what we just started, it's about 8 weeks old, and we discovered that some of the ratings were not well suited. Basically, a small number of people were exposed to a very large number of choices, right? So in the movie situation, you have a large number of people watching a small number of movies, right? Comparatively small. So there's some kind of the data is not structured like that. In here, for example, in pet recommendations, what you have is a small number of people, about 500,000 people buying about 8 million pets. So there's that mismatch. We had to deal with that. So we are trying some techniques to improve the structure by putting people in certain clusters and trying to run things like that. So the other thing is basically currently what we've deployed is an internal description, like the document case. We just came up with a bunch of internal descriptions, and so that is easier. Like we it is easier, and it's for bootstrapping. When you have no data, it's better to go with the internal description method. And it's also good for business control, right? You suppose the product manager says, I want these kinds of people to be recommended, or this much value in pet cash spent. So those things you can modify things and send people on different directions. So that's so what was all that the Wikipedia entry about all those squiggly numbers? So I just I just want to give you some idea about what are the things that can go wrong. So why do you need all those mathematical support just to factorize matrices? Basically, scaling is very hard, and if you just rely on the virtual memory, it would probably take months, because the access pattern is such that everything needs to be in memory at the same time to compute even just one point in the matrix. So everything would have to be pushed into the memory, pushed out. So it'll take several months, and so yeah, we have some methods to overcome that. Instead of just doing a standard SVD, do a stochastic gradient descent, which just is more of a serialized method. And encoding features is you understand it as you go. It's there's no book written about how to encode features, and what happens when you encode it like that. So it's just that you encode it, and you see the output. It's more of how much experience you have. So that's something that can go wrong. And getting a good fit with the context, right? So that is just like you have these methods, and you have something like pet recommendations, and you have to understand the context and see how do you want to fit that in this particular context. So those are things that are not quite clear, and won't be clear ever. So that's where the people have to work. and whether you kick ass or you get your ass kicked depend on the particular this following thing. Basically, for every recommendation that you want to make, you're going to compare that against like with 1 million people. So if you want to find out how similar I am to who are the top 10 similar people to me, then I have to basically run a loop with me and like 1 million people, and that is the most intensive loop, and that sometimes needs to be done in real time. That's not always possible. That usually the first time I did it took me about 4 seconds. And yeah, so right now at tag we have a target of 1,000 recommendations per second without using millions of servers, of course. So the way you do it is, for example, not to use for loops. That's when you start, you just write a for loop. That's very naive. What you use is you use libraries like NumPy, and you just don't think about things in terms of for loops. You just think about them in terms of linear algebra. So a matrix is a highly functional data structure. What happens in one point in a matrix doesn't affect all the other points. So it's a very highly functional data structure, like functional as in functional programming. So if we stick to that abstraction, the whole pipeline kind of understands that. Underneath NumPy, and then there are a bunch of Intel optimized libraries that kind of understand that. So what they do is they just load everything into all the cores and do it in one operation, instead of just for looping to a million times. You just do everything in one process cycle if you have enough RAM and enough number of CPUs. Right? So yeah, so those are the things. This is Atlas is just automatic tuning of linear algebra software. What that does is it just looks at your particular CPU architecture, and it tries to it'll probably, when you start running it the first time, it'll configure it for like a couple of hours, and it will understand everything about your processor, like how much cache it has, and how long it takes from cache to the actual processor, things like that. So once you go that route, things can get pretty fast. And currently we have, for one recommendation, we have about 16 milliseconds. So that's the current benchmark that we have. And when you think about mostly all the implementation in Python, and when you think about Python, people think about it as a dynamic, slow programming language, but that's not really true, because when you code to the linear algebra abstraction, and when you code using NumPy, basically what you're writing is pure C, right? That you can't try to rewrite it in C and try to get faster performance. It's not going to happen, because what's already happening is it's meeting the metal at some level. So, and Python is also pretty popular among engineers for some reason, and I mean, I have an idea, but I'm just so if you see, this is the number of people who like it, and the blue is the hate, and you can see on the other end, this was a poll conducted by Hacker News, actually, about 30,000 people voted, and on the other side, you have Visual Basic, like the most hated language, and you have like, and yeah, programmers are very political when it comes to programming languages. Yeah, it's a pretty interesting graph. And all these languages, Lisp, Haskell, Clojure, are pretty on the fringe. Nobody is mainstream is adapted. So people usually love these languages, but I've never seen them deployed widely. But in here, Python is like an outlier, complete outlier, that people actually like it, and it's actually widely deployable, applicable, and things like that. So yeah, so let me just make a quick demo. It's going to be, I don't know how to keep this. Yeah?
Visual Basic is worse than COBOL.
Yeah.
Is COBOL listed there?
Yeah, it's a second.
Oh my god, there it is.
Yeah. Java, PHP.
That's awful.
I actually have a large C++ C. See that?
C is pretty popular here. C++ is really bad, yeah.
PHP beats Java.
Yeah.
Well, it's interesting that PHP and Java are about equally hated.
It's pretty fun.
I don't think Richard agreed with this one.
No, I didn't hear them all.
That's because you have taste.
Yeah, just let's run a quick demo. This is just something that I wrote using a for loop, this particular first program. So I'm just making a 300 by 300 random matrix, two matrices, and I'm going to time them, and you can already see it's going to take a while. Kernel busy. Awesome, 8 seconds. And that's just a 300 by 300 matrix. And we usually deal with a million by 100,000 matrices. So that's not going to work. So when it comes to NumPy, I'm just going to time it. Takes about 2 milliseconds. So, and this particular system doesn't even have Atlas installed in it. And if you have Atlas installed, it will be less than milliseconds. You know, 100th of a millisecond, something like that, to do that operation. So when you think about Python, don't think about think about NumPy. And this is actually criminal to write for loops and things like that, and expect things to work. And so that's just something to keep in mind.